Okay, in the last section, we uncovered the sum and difference identities for cosine. So specifically, those were these identities. So I often refer to these identities as cosine, cosine, sine, sine identities, as I find calling them that is helpful simply for remembering the form, cosine, cosine, sine, sine. And the operator in the middle is the opposite of the operator out here when the identity is unwrapped. So what we're after today is analogous identities for sine and indeed tangent. So let's start with sine. Can we find an identity that unwraps the sine of a plus b? So that would be the sum identity for sine. And yeah, we sure can. We could go through a proof that's analogous to what we did with cosine by drawing the unit circle and picking a bunch of points and then going through all of this lovely algebra that we did.
Please, no! No! No!
But now that we have the sum and difference identities for cosine, we can use those to determine the sum and difference identities for sine very easily, because cosine and sine are very closely related to each other. So in particular, let's suppose you have a right triangle, and you have an angle here, theta, in that right triangle. Now we know that the sum of the angles in a triangle add up to 180 degrees. And 90 degrees is taken up by this 90-degree angle right here, which means that theta and this angle up here are complements. They themselves add up to 90 degrees because there's only 90 degrees left to distribute among them. So, however, in the universe of radians, which is really what we're working with in this chapter, instead of calling this guy 90 degrees minus theta, which is the complement of theta, let's call it pi over 2 minus theta. Okay, well that's all well and good. But what does this tell us? Well, let's look at theta and let's ask ourselves what the sine of theta is. We can see that the sine of theta is, of course, opposite over hypotenuse. So this side over this side. Now, that is the same thing as relative to this angle, adjacent over hypotenuse. Right? So for this angle, the adjacent side is the opposite of the angle theta, which means that sine of theta, which concerns these two sides, is equal to the cosine of the complement of theta, or pi over 2 minus theta, which concerns those same two sides. So how is that going to help us find a sum and difference identity for sine? Well, let's see. Well, sine of a plus b, which is what we want an identity for, is equal to cosine of pi over 2 minus a plus b. Right? Sine of stuff is cosine of pi over 2 minus that stuff. All right, well, let's distribute the negative inside this cosine. So we have cosine of pi over 2 minus a and then minus b. Okay, but moreover, why don't we associate these first two terms as a single number? So we're going to just think of pi over 2 minus a as a single thing, and then minus b. So it's like cosine of one object minus another object. Well, we have an identity for that right here. Cosine of one thing minus another is cosine, cosine, sine, sine. So yeah, let's use that. So we're going to get cosine of that first thing, which is all of this, times cosine of the second thing, which is b. This minus becomes a plus, and then we're going to have sine of the first thing and sine of the second thing. Okay, well, cosine of pi over 2 minus a, that's just sine of a. And sine of pi over 2 minus a is just cosine of a. So here we are. We have uncovered an identity for sine of a plus b. So this is officially called the sum identity for sine. I often refer to it as simply sine, cosine, cosine, sine, because again, the name sine, cosine, cosine, sine is helpful for remembering, obviously, the form of this identity. So, all right, well, what about sine of a minus b? Well, sine of a minus b would be sine of a plus negative b. So it's like replacing everything in this identity with negative b. So we're going to have sine, cosine, plus cosine, sine. Okay. But remember, cosine of negative b is equal to cosine of positive b. So we can just write that as sine, cosine. And remember that sine of negative b is negative sine of b. So this negative here kind of pulls out all the way to the front of that term. So we can have minus cosine sine. Okay, so this is sine of a minus b. All right, so take a look at these two identities. Notice the pattern is the same. It's sine, cosine, cosine, sine. And however, unlike with the cosine case, for sine, the operator is preserved. So sine of a plus b gives us a plus here, and sine of a minus b gives us a minus here. So yeah, let's write all these down now. So for cosine, it's cosine, cosine, sine, sine. And of course, the operator is the opposite. For sine, it's sine, cosine, cosine, sine. And the operator is the same. So sine, cosine, cosine, sine. And in every case, it's always the first angle, the second angle, first angle, second angle. So AB, AB. So sine of a minus b will be sine, cosine, cosine, sine. You may feel a little silly, but seriously, I do recommend actually chanting these identities to yourself the first few times that you're using them, and then you won't need to look anything up again. They'll just come naturally to you. You'll always be able to write them down and call them when you need them. So, okay, there are two more for tangent, and we are not going to go into the proofs of the tangent one, but I'll just sketch the basic idea. So if you have tangent of a plus b, you can write it as sine of a plus b over cosine of a plus b, and then unwrap each of those in turn. Because we know how to unwrap sine of a plus b, we know how to unwrap cosine of a plus b. Then there's some algebra that you would do to turn everything back over into tangents, and eventually you would simply arrive at this particular form, and that is this guy. So this is the sum identity for tangent, and the difference identity for tangent is virtually the same, but with the operators in the opposite place. So it's a minus on top and a plus on bottom. Okay, and I often refer to these two identities as tan over 1 tan. So tan over 1 tan. So that's cosine, cosine, sine, 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 cosine, cosine, sine, and tan over 1 tan. And there we go. I never forget those. All right, let's find the sine of negative 15 degrees. Now, negative 15 is not one of our special angles. So like we did before with these problems in the last class with cosine, we have to find two angles that we are familiar with that add or subtract to give negative 15 degrees. So you could go, say, 30 degrees minus 45 degrees, or 45 degrees minus 60. Let's go with the 30 minus 45. And now we have a sine of a minus b, so we can use the sine, cosine, cosine, sine identity. So this is sine, cosine, cosine, sine. And it's always first angle, second angle, first angle, second angle. So sine, cosine, and then the minus here stays as a minus. For cosine, it switches to a plus, but for sine, it would stay as a minus, right? So sine, cosine, and then cosine, sine. So cosine of first angle, sine of second angle. Okay, so now each of these factors we know how to work out. Let's put down these answers. Sine of 30 degrees, we know that's 1/2. Cosine of 45 degrees is rad 2 over 2. Cosine of 30 degrees is rad 3 over 2. And sine of 45 degrees is rad 2 over 2. Okay, so this is rad 2 minus rad 6 all over 4. And that's our final answer. And again, notice that the quantity rad 6 is larger than the quantity rad 2. So if you have rad 2 minus rad 6, then that's going to be a negative number in the numerator. So that means this entire quantity is negative, and that makes sense because negative 15 degrees is in the fourth quadrant. And in the fourth quadrant, only cosine and secant are positive. So everything else, including sine, would be negative, as we of course have here. All right, so here we're going to evaluate tangent of 13 pi over 12. And of course this is in radians, but the basic idea is still the same. We are looking for two angles with which we're familiar that add or subtract to 13 pi over 12. So we could just start playing around, like maybe 12 pi over 12 plus pi over 12. So that adds up to 13 pi over 12. 12 pi over 12 is pi, and that's an angle we know and love. But pi over 12 is not one of our, special angles. So we can scratch this one. So maybe 11 pi over 12 plus 2 pi over 12. So yeah, 2 pi over 12 is pi over 6. That's a good one. But 11 pi over 12, no bueno. So how will we ever get this to work? Let's try this one. Certainly this adds up to 13 pi over 12. And what do we have right here? 10 pi over 12 is 5 pi over 6. That's a good guy. And 3 pi over 12 is pi over 4. That's also an angle we know. So yeah, we found it. So that means that this is equal to tangent of 5 pi over 6 plus pi over 4. Okay, and now we can use the tan over 1 tan identity to unwrap this. So tan over 1 tan. Okay, so again, it's still first angle, second angle, first angle, second angle. So yeah, to finish this problem, we just need to evaluate each of these 4 pieces and then clean up what we have. So tangent of 5 pi over 6. Well, that's the second quadrant, and tangent's negative in the second quadrant. So this will be negative rad 3 over 3 plus tangent of pi over 4. That's positive 1. And the denominator is 1 minus tangent of 5 pi over 6, still this. And tangent of pi over 4 is, of course, 1. So what we have is negative rad 3 over 3 plus 1 over 1 plus rad 3 over 3. Okay, So we're done with the trigonometry part of this, but of course we should clean this up because we have fractions within fractions and we have an unrationalized denominator. So let's handle both of those things. So if we multiply the top and the bottom by 3, which is the mini denominator within these little mini fractions, then when the 3 distributes to everything, it's going to clear out those fractions. So we're going to get negative rad 3 plus 3 over 3 plus rad 3. All right, so now we need to rationalize this because we have a radical in the denominator. And when you have more than one term in the denominator and you need to rationalize it, the particular move is to multiply by the conjugate of the denominator. So the conjugate being, this was 3 plus rad 3, so we're going to multiply everything by 3 minus rad 3. The effect is that in the denominator, you have the difference of squares formula, a plus b, a minus b, so you're going to get 3 squared minus the other thing squared. And that's going to eliminate the problem of having a radical down there. In the numerator, we just need to actually FOIL this. So we're going to get negative 3 rad 3 plus rad 3 times rad 3, which is 3, plus 3 times 3, which is 9, and then minus 3 rad 3. Okay, so what do we have here? 3 plus 9 is 12, and then we have negative 3 rad 3 minus 3 rad 3, which is minus 6 rad 3. In the denominator, we have 9 minus rad 3 squared, which is 3. So in the numerator, we can factor a 6 out, giving 2 minus rad 3. And in the denominator, 9 minus 3 is indeed 6. So here these 6's cancel, and we actually get our final answer, which is 2 minus rad 3. And this really shows you that it is worthwhile to not only clear fractions when you have fractions within fractions, but to rationalize denominators. Because if we didn't and we just stopped at this business here with all the rad 3's, we would have completely missed out on this significantly more straightforward, simple final answer. So always rationalize your denominators. All right, so here again, we have one of these situations, but there are 3 distinct angles in this problem. A, B, and the angle A minus B. We know that we should use the sum and difference identity for sine, right? So that would be sine of A minus B is sine, cosine, cosine, sine. Okay, so all we have to do to answer this question is figure out each of these 4 ingredients, and 2 of them were given right away. Cosine of A was given as negative 7 over 25, so we've got it right there. And sine of B was given as negative 3/5, so we've got that one to put right there. So that means all we have to do is find sine of A and cosine of B. So we'll start by finding sine of A. We're given cosine of A, and while we're not explicitly told what quadrant A is in, we are given some information about it. And, oh, actually, that information's pretty clear, isn't it? Between pi and 3 pi over 2 is quadrant 3. I thought we'd have to do a little more hacking to get it, but there it is. So we can see that A is in quadrant 3. And that means that sine of A will be negative when we figure it out, because sine is negative in the 3rd quadrant. So you can use a Pythagorean identity between sine and cosine, or draw a triangle. So I'm just going to draw a triangle. And we know that cosine of A is negative 7 over 25. So of course on a triangle we will only put positive lengths. Cosine concerns adjacent over hypotenuse. So we'll use the Pythagorean theorem to find the missing side over here. Call it little a. And we know that a squared plus 7 squared is 25 squared. $625 minus 50 is 575, but we got to add 576, because we actually subtracted 49. So a squared is 576, and therefore a is the square root of that, which is 24. Okay, so now we can read anything we want, sine, cosine, tangent, whatever. So sine of a is what we're after, and we know that it's opposite over hypotenuse, right? So of SOHCAHTOA. So that's 24 over 25, but we remember that we need to assign the negative because a is in the third quadrant. So there's our sine of a, and the last ingredient that we need is cosine of b. So, all right, well, what about b? We can see, again, from the given information that b is in the fourth quadrant, between 3 pi over 2 and 2 pi. So we've got L triangle here, and we're given that sine of b is negative 3/5. Of course, sine concerns the opposite and the hypotenuse, so you may recognize this as a 3, 4, 5 triangle. You can calculate the base of this triangle, of course, just by what we've been doing with the Pythagorean theorem. So here we'll get the square root of 25 minus 9, which is the square root of 16, which is 4. Okay, so that means that cosine of b, which is what we're after, is going to be adjacent over hypotenuse, so 4 over 5. And again, because b is in the fourth quadrant, this is positive. All right, so putting it all together, again, we are after sine of a minus b. So that's sine, cosine, cosine, sine, and we have all 4 of those pieces. So sine of a we worked out as negative 24 over 25, and cosine of b we worked out as positive 4 over 5, and cosine of a was given to us as negative 7 over 25, and sine of b was given to us as negative 3/5. So we just have to do this calculation and then we're done. Okay, so negative 4 times 24 is negative 96. And then negative 7 times negative 3 is 21. This is all over 25 times 5 is 125. So negative 96 minus 21, that's negative 117 over 125. So there's our final answer. All right, for our last example, we are asked to verify this identity. And as usual, you want to start with one of the sides, and usually the more complicated side, and play around with it until you kind of arrive at the other side. So there's a good argument to be made for choosing either of these sides to start with. They're both pretty complicated looking. But I would say the left-hand side is definitely the one we really do want to start with, because there's a really clear directive on what to do right away. Because we have tangent of a thing plus a thing, tangent of a thing minus a thing, so we can go right in and use the tan over 1 tan identities, see what this is going to look like. So let's do that. Start with the left-hand side. Of course, our first step is just to write down that actual side, but at no point in our proof will we equate this with the right-hand side. So we just have the left-hand side written, and now let's play with it. So of course, here we can use the tan over 1 tan tan identity. And same thing here. Notice the only real difference between these two big terms is the position of the pluses and minuses. Okay, well, we can evaluate tangent of pi over 4 because that equals 1. And that shows up in a bunch of places here, doesn't it? So what we have is 1 plus tangent of t over 1 minus, and again, tangent of pi over 4 is 1. So this is just 1 minus tangent of t. And this one we have 1 minus tangent of t over 1 plus tangent of t. So why don't we push these into a single fraction using a common denominator? So the common denominator here would be 1 minus tangent times 1 plus tangent. So that means that this particular term here will get multiplied by 1 plus tangent over 1 plus tangent. Which will manufacture that common denominator for that term. And this particular guy is going to get multiplied by 1 minus tangent over 1 minus tangent. So, all right, what do we get here? If we FOIL out everything in the numerator here, we're going to get 1 plus 2 tangent plus tangent squared of t. And in the denominator, we're going to get 1 minus tangent squared t. And foiling out the numerator here, we're going to get 1 minus 2 tangent t plus tangent squared t. And in the denominator, we'll get 1 minus tangent squared t. So now we do have a common denominator, of course, so we can just write this as one big long fraction all over 1 minus tangent squared t. This is good news, by the way, because if you look at the original problem, we're trying to get this thing to look like that. And that has a denominator of 1 minus tangent squared. So you can kind of tell we're on track. All we need to do is make the numerator somehow look like 2 times secant squared. Okay, so returning to our work, we have 1 plus 2 tangent t plus tangent squared t plus 1 minus 2 tangent t plus tangent squared t. So we can certainly see that this term will cancel with this term, and we can add 1 plus 1, that gives us 2, and tangent squared plus tangent squared gives us 2 tangent squared. Okay, super cool. We can factor the 2 out of this, which gives us 1 plus tangent squared over 1 minus tangent squared. And hey, 1 plus tangent squared, that's a thing. I tan secretly. So we'll use that, and in fact, that is the right-hand side of our identity. So we're done. Hooray!